Yeah, all right, I guess we're good. So let's talk about sequences. Today is April 20th. Sequences. So let's start off with something easy. So a sequence is just a way of writing a pattern. Let's say we're going to have a sub n equal to 2n over n plus 1, which might feel pretty straightforward. Sometimes we're asked to write out the first few terms of a sequence. I don't find this particularly useful most of the time. That's not true. It is useful sometimes. So we can write out the first few terms. So we can say like a1 is just 2 times 1 over 1 plus 1, which is 2 over 2, which is 1. Well, no, that's not true. I find it kind of cumbersome to keep writing out a sub 2 or whatever, but we'll do that the first few times. So a sub 2 is just 2 times 2 over 2 plus 1, which is 4/3. A sub 3, 2 times 3 over 3 plus 1, which is 6 over 4. What I really want you to see about the sequence is it's really just acting like a function where we input something and we get something out. Come on in. The only difference between Andrea. Not between Andrea. The only difference between a sequence and a function is that for any old function, you can plug in whatever number you want. Whereas for a sequence, we only plug in integers like 0, 1, 2, 3, 4, 5, 6, etc. So that's really kind of the only difference. We could keep going. A4 is going to be 2 times 4 over 4 plus 1, and so on and so on and so on. Most of the time, what we actually care about when you're talking about a sequence is what does the sequence converge to? What, if anything, does an equal to 2n over n plus 1 converge to? What we're really asking here is we're asking about the behavior of this formula or this sequence as the inputs, as the n's get really, really large. So this question, what does it converge to? Really the question we're asking is, this is asking, what is the limit as n gets really, really large of your sequence 2n over n plus 1? That's the question that's actually asked. So when someone asks you, does the sequence converge or diverge? They're really saying, take the limit as n goes to infinity, meaning let n get really, really big. Here's the problem, at least the problem with this one. If n gets really, really big, both the top and the bottom are really, really big. If I plug in infinity, although it's kind of weird, I'm going to get infinity over infinity. Okay, technically I have 2 times infinity, but 2 times infinity is infinity. And on the bottom I have infinity plus 1, but infinity plus 1 still infinitely large. So we often kind of manipulate infinity without really doing it. When you have an infinity over infinity form, which is called an indeterminate form, it kind of means anything can happen. And to deal with that, we're going to use some tricks. A real common trick when dealing with a limit like this is to divide everything in the top and the bottom by n to the highest power that is in the denominator. So to evaluate this limit, we're going to do this. The limit n goes to infinity of, I'm going to do 2n divided by n over n divided by n plus 1 divided by n. Still the same thing, right? I've just divided, I like to say multiplied. I've multiplied the top by 1 over n, and I've multiplied the bottom by 1 over n. But now we're going to simplify. When we simplify this, we're going to get the limit as n goes to infinity of 2 over 1 plus 1 over n. And here's something that's going to come up all the time when we talk about limits or sequences converging. As n gets really, really exceptionally large, what happens to 1 divided by n? Does it get big or does it get small? Small. And that happens all the time. If a fraction has a denominator that's getting really, really large, come on in, the whole fraction gets really, really small. I like to think about it this way. I've got $1 and I'm trying to divide it between 1 million people. You're not going to get very much if you divide $1 into 1 million different parts. You're going to get a fraction of a cent. So that $1 divided by something infinitely large becomes infinitesimally small, closer and closer and closer to 0. And this limit ends up being 2 over 1 plus 0, which is 2. This sequence doesn't ever actually equal 2, but it gets closer and closer and closer and closer to 2. So that's the general kind of idea with any sort of sequence. If you want to see what its limit is, if you want to see what it converges to, you do that by taking one. Also, as I said before, but just in case you remember, please feel free to ask questions. Like if you have questions, something isn't clear, let me know. I will try to clarify anything. All right, Lily? Yes, okay. And remind me of your name. Yeah. You too? You're Lily as well? Oh, both Lilies. Ah, okay. Sorry. I got both in one shot. So let's look at a few more examples. So let's say I have this sequence. A sub n equal to 5n over 2n squared plus 3. Whoops, can't see that. There we go. And again, we can write out some terms. If I'm going to write out terms, instead of writing a1 equals, a2 equals, I like to just start writing them out. So if I was going to write out terms, I would say, okay, my terms are going to be, well, if I plug in 1, I'm going to get 5 over 2 plus 3, which is 5 over 5, which is 1. And the second term is going to be 5 times 2 over 2 times 4 plus 3, which is 10 over 11. And my next term is going to be 5 times 3 over 2 times 9 plus 3. I don't really like simplifying these after a while. They just kind of get to be ugly. But we can certainly, right, to plug in or to find them, we're just substituting in n equal to 1, n equal to 2, n equal to 3. If I plug in 4, 5 times 4, 2 times 4 squared plus 3. That's just going to be 20 over, I don't know, 2 times 16 plus 3. So to find the first 5 terms of a sequence, you're just plugging in n equal to 1, 2, 3, 4, and 5. Most of the time, a sequences are going to start at n equal to 1. Doesn't have to. You can start anywhere, really. I guess I should do the 5th one, just because a lot of these questions on your homework are like, find the first 5 terms, find the first 6 terms. So the 5th one, a sub 5 is going to be 5 times 5 over 2 times 5 squared plus 3, which is just 25 over 2 times 25 plus 3. Nice thing about web work, you don't have to simplify stuff to input it. So you could totally write an unsimplified answer and it's going to be totally fine. But then the more interesting question, the question that we really care about a lot of the time is, what does this converge to? Or does it diverge? So we say a sequence converges if its limit as n goes to infinity is some real number. We say a sequence diverges if its limit is either infinity or negative infinity, or maybe it bounces back and forth between 2 different numbers forever and ever and ever. We'll see a couple of examples of that in a few minutes. So I'm going to apply the same technique I did to the previous problem. I'm going to take the limit as n gets infinitely large of 5n to n squared. I'm going to divide. So once again, this is an infinity over infinity type. The top's getting infinitely large. The bottom's getting infinitely large. The way I'm going to deal with that is to divide everything by n squared. So I'm going to say that this is equal to the limit as n goes to infinity of 5n over n squared, 2n squared over n squared plus 3 over n squared. And I do think it's worth our while to simplify these expressions. 5n over n squared reduces to 5 over n. 2n squared over n squared reduces to 2. And 3 over n squared doesn't reduce, it just stays as 3 over n squared. Yeah. So the way I would phrase it is I'm dividing every term by the n to its highest power that occurs. Now I'm going to be a little bit, I'm going to bring that back just a tiny bit. We're going to see in the future example, we're really dividing every expression by the highest power of n that is in the denominator. So if you had a higher power in the numerator, we wouldn't pick that. Yeah. And that's that. And again, I'll say that this works as long as your numerator and your denominator are just powers of n. And it doesn't work if you have other types of functions like trig functions or logs or anything weird like that. Good, Chelsea? Yeah. Yes, I'll repeat it many times. But we say a sequence converges if its limit is a real number, meaning it gets closer and closer to one specific real value. We say a sequence diverges if the limit doesn't exist, meaning it could bounce back and forth, or the limit could be infinity. If a limit's infinity, we say that that limit doesn't exist. We're just being more specific about the way in which it doesn't exist. We'll do an example of that in just a moment, I promise. So here, as n gets really, really large, 5 over n is going to be infinitesimally small. That's going to go to 0. So is 3 over n squared. Because as we're going to see over and over and over again, fractions where the denominator gets really, really big, the overall, that fraction itself gets really, really small. That's 0 over 2 plus 0, and 0 divided by 2 is 0. And I would say this makes sense to me and will make sense to you because the denominator is growing faster than the numerator. So that fraction is getting small, closer and closer to 0. On the other hand, in our previous example, the denominator was and the numerator were getting big at rates that were in proportion to each other. The numerator was getting big twice as fast as the denominator. So that's why our limit ended up being 2. Okay. Let's look at some more examples. Come on, papers. So let's see. Yeah, we'll go back in a second. Let's say we had something like our sequence equaling, I don't know, 4n cubed plus 5 over 2n squared plus 3n plus 1. I don't really want to write out terms, but I will point out that we certainly could. We write out terms. We're just plugging in. So, right, my first term would be 4 times 1 cubed plus 5 over, it feels silly to write 1 to any power because 1 to any power is just 1. I should really just write the bottom as 2 plus 3 plus 1. And my second term would be 4 times 2 cubed plus 5 over 2 times 2 squared plus 3 times 2 plus 1. Kind of gnarly, right? The terms just don't get nice. 4 times 3 cubed plus 5. Okay, I think we've had enough of this. And they go on and on. And if you want, we can certainly talk about the labels. That's a sub 1. That's a sub 2. A sub 3. And so on and so on. We're really just plugging in the next integer, or what's called the index, to keep finding the next term. What about convergence or divergence? Well, we're going to take the limit as n goes to infinity of 4n cubed plus 5 over 2n squared plus 3n plus 1. Now, what I'll tell you is, looking at this, would expect the limit to be large because the top thing is a thing that's growing faster than the bottom thing. N cubed gets bigger faster than n squared. So, and I don't really care about the constants. 4n cubed gets bigger faster than 2n squared. But I will say I am only really paying attention to the highest powers in the numerator and the denominator. Here, we're going to be smart about it. We're going to divide everything by the highest power in the denominator. This isn't super as important for limits of sequences. It becomes much more important when we start talking about limits of just functions in general, and we start going to either infinity or negative infinity. So that's why we're setting the stage so that we can be successful later. So we're going to divide everything by n squared. So we're going to get 4n cubed divided by n squared plus 5 divided by n squared over 2n squared divided by n squared plus 3n divided by n squared. I think you can, if you're comfortable with skipping this step, you're certainly welcome to skip this step and just say, oh yeah, I know that 4n cubed divided by n squared is just going to be 4n, and 5 divided by n squared stays as 5 divided by n squared, and 2n squared divided by n squared is 2, and 3n divided by n squared is 3 over n, and 1 over n squared stays as is. It is totally reasonable to skip this step here and jump straight to that step there. If you wanted to, you can even say you're going to do the thing where like you're multiplying the top and the bottom by 1 over n squared. And then, as it has in the last two times, if n is going to infinity, the things that are getting divided by n or powers of n are going to 0. So here's what I would write, and I do think it's okay to write this. This limit is going to be 4 times infinity, because that n left there is still there, plus 0 over 2. 4 times infinity is infinity divided by 2 is still infinity. Okay, so let me ask you all a question. Not the best question ever, but it's an important question. Does this limit exist? And the answer is no. This limit does not exist. But we are going to be more informative about our answer. So although this limit doesn't exist, it is also true that this sequence gets infinitely large as n gets larger and larger and larger. But for a limit to exist, the sequence has to get close to one specific real number. Finite real number, maybe you should sometimes say. That's not happening here. This function right now, you can pick bigger and bigger values of n, and you're going to get bigger and bigger outputs. Is there a question, Maria, or no? So even though this limit doesn't exist, we will say the limit is infinity because that's what we are asked to do typically in level. I would also point out that this sequence, one second, Teresa, this sequence an equal to 4n cubed plus 5 over 2n squared plus 3n plus 1 diverges. And that's all I would usually say, but then if someone asked me to say more, I would say it diverges to infinity, which is often what web work is asking you to actually input. Sometimes the sequence will diverge to infinity, sometimes the sequence will diverge to negative infinity, and sometimes it will just diverge, and you can't say in what direction it diverges at all. So what I said, and that's actually good clarification. So in general, if n is getting large, I would say n goes to infinity, then 1 over n to any positive power, sorry, can you not see that very well? 1 over n to any positive power is going to get small. That's going to go to 0. Because they're kind of inversely related. If n gets big, 1 over n, or 1 over n squared, or 1 over n cubed, or it doesn't even have to be 1, right? It could actually be any constant if you really want. K over n to any power, where p is positive, is going to go to 0. Because you're just dividing by something that's getting bigger and bigger and bigger and bigger and bigger. Cool. Oh yeah, we should look at those too. Other questions? Yeah, there's some good questions. You're always welcome to take pictures. I will also mention I do post all of these on Google somewhere, the Google Drive, and they're linked from various places. That's it. Don't let me stop you from taking pictures. Just know you don't need to if you don't want to, really. Okay, other things. Let's see. Yeah, let's look at this here. Let's say we have a sub n equal to -1 to the n plus 1 times 3n plus 1 over n plus 1. Oh, can't see that. Sorry. Okay, so this sequence is definitely alternating. And the -1 to the n or the -1 to the n plus 1 or n minus 1 indicates something like that. You see something like that, we know that we're changing signs every other term. Or I guess every term. So I could write out some terms. Let's see. A sub 1 is going to be -1 squared times 4 over 2, which is just 2. A sub 2. So I know I don't want to write -1 cubed because I know that once the first term is positive, the next term is going to be negative. And the next term is going to be positive. And the next term is going to be negative. But I know my next term is going to be negative, and I'm just going to plug in 2, and we get 7/3. And then my next term is going to be positive. And here's what I really actually would love for you all to see. I don't really want to plug in. What I want you to see is that every time n gets bigger by 1, the top is going to get bigger by 3. I'm multiplying it by 3. So I should think about, oh, well, it was 4 and then 7. The next numerator is going to be 10, which I will get if I plug in 3. 3 times 3 is 9, 9 plus 1 is 10. Similarly, the bottom is just increasing by 1 every time. So here it was 2, here it was 3, here it's going to be 4. And the next term, I should be able to just say it's going to be negative. Top gets bigger by 3, the bottom gets bigger by 1. Oh, so that's a sub 4, not a sub 5, sorry. And then a sub 5 is positive. The top gets bigger by 3, the bottom gets bigger by 1. And you can keep doing that over and over and over again. Really, the reason I'm saying it is because later on, we're going to talk about starting with the sequence and working backwards to get the formula for the sequence. And if you can see that the top or the bottom is increasing by the same amount every time, you're going to have that amount times n in your formula. Okay. Okay. Welcome, Dana. Oh, let me do, sorry. Pin my video there. And oh, by the way, before I forget to mention, please do at some point scan one of the 4 laminated attendance forms and fill out the attendance form. Even if you're not registered officially, everyone's filled out the attendance form. Yeah, it's like, sorry. So I was getting away from myself here. So this sequence, if I look at the non-alternating part for a second, we can see that the limit as n goes to infinity of 3n plus 1 over n plus 1, I think it's going to be 3. Let's check. Yeah, if I divide everything by n, I get 3 plus 1 over n over 1 plus 1 over n. I didn't show my work. I said I multiplied by 1 over n over 1 over n. And then that's going to go to 3 plus 0 over 1 plus 0, just 3. I want to be very specific here. I'm not saying the sequence converges to 3, because I didn't find the limit of the sequence. I found the limit of the non-alternating. What's happening is the alternating sequence is bouncing back and forth between things that are getting closer to 3 and things that are getting closer to negative 3. So if we went way further out and said, like, you know, the 100th term here is going to be negative 1 to the 101, which is negative 1, times 301 over 101, which is pretty much negative 3, approximately. And the next term, the 101th term, 101th, 101st. I think 101st, not 101. 101st term is going to be positive 304 over 102, which is essentially positive 3. We're going back and forth between 3 and negative 3, and we're not getting close to any one single specific value. And when that's the case, we have to say that the sequence diverges, because we're not getting close to one single value. We're getting closer and closer to 2 values that are not next to each other. So this sequence definitely diverges. And that's all we can say, because it's not diverging to infinity. It's not diverging to negative infinity. It's oscillating back and forth between things closer to 3 and things closer to negative 3. Yeah, Shereen. Sorry, say that one more time. A sub 101. Oh. Yeah, sorry. Yeah, I know. I started right 100 and then I know. My writing is not always excellent. But yeah, that's A sub 101. Yes. Yeah. Let's do that. So yeah, a couple more. Got lots more actually. Let's say we had the following. So let's say we had a sub n equal to, sure, I'm going to make it kind of gross. Yeah, 12n to the 5th plus 4n cubed plus 5n squared over 4n to the 5th plus 6n to the 4th plus 7n. Okay. Question, Lila. Yeah. Yes, with one exception, which I'll come back around to in a minute. But yeah, typically, if you're alternating back and forth between positive and negative numbers, you're not getting close to one specific number. There's one exception. We'll get to that in a little bit. So this one here, we could do the thing we've been doing every time. But what I would like for you all to see is that when you have a rational expression where you have positive integer powers of n or positive integer powers of n, if the highest power in the numerator and the denominator is the same, then the leading coefficients are what we're going to end up getting as our limit. Or I should say, the quotient of the leading coefficients. So this limit is going to end up being 12 over 4, just 3. We can, bless you. We can definitely see that if we do it, right? Here's the work. Limit as n goes to infinity of, all right, 12n to the 5th plus 4n cubed, 5n squared over 4n to the 5th plus 6n to the 4th plus 7n. I'm going to divide everything by n to the 5th. Or alternatively, you can think of it as multiplying the top and the bottom by 1 over n to the 5th. We do that, we're going to get the limit as n goes to infinity of 12 plus 4 over n squared plus 5 over n cubed over 4 plus 6 over n plus 7 over n to the 4th. And each of these things that are being divided by n, as n gets really, really big, those all go to 0. Now I should stress that only happens as n goes to either infinity or to negative infinity. Later on, when we start doing limits where like x approaches 3, we can't say that something divided by x to a power is going to go to 0. Only if x is getting infinitely large or negatively infinitely large. So this ends up being 12 over 4, which is 3. This idea is pervasive, meaning when you're finding a limit of something, whether it's a sequence or a function or whatever, it is often very useful to divide everything by the thing that gets biggest the fastest. Well, let me give you another example. Let's say we want to find. So I'm kind of being a little loose here, and I should have said this sequence converges to 3. When you find the limit equal to 3, we often stop just saying, but yeah, this converges to 3. Or let's look at a sub n equal to 3e to the 2n plus 4e to the n plus 1 over e to the 2n plus e to the negative n. Ooh, there's a bunch of things that are getting big as n gets big. As n gets really, really large, e to the n, e to the infinity is infinity. E to the 2 times infinity is also infinity. Ooh, what's e to the negative infinity? This is actually something we should point out here. Here is your graph of e to the x. And as x gets really, really large, e to the x gets really, really large. So the limit as x goes to infinity of e to the x is infinity. But if x gets really, really negatively large, meaning we're going way out to the left, e to the x gets closer and closer and closer to 0. So when you have e to a large positive power, it's getting very large. When you have e to a large negative power, it's getting closer and closer to 0. So when I'm looking at this, I'm thinking, oh, there's something that's going to infinity. There's something that's going to infinity. There's something that's going to infinity, but that's going to 0. I still have an infinity over infinity, though. We have infinity divided by infinity. Indeterminate. We don't know. We have to do something. So I'm going to, just like here, I divided everything by the thing that was getting the biggest, the fastest. I'm going to do the same thing here. I'm going to divide everything by e to the 2n, because that's the thing that is getting biggest, the fastest. I know I say divide, but I really prefer writing it as multiplying by the reciprocal. Whatever way is more comfortable for you. You can write division, that's totally fine. So writing this out, we're going to get, I should have written the limit though. Right, make sure you write the limit every step. So I'm going to write the limit n goes to infinity of 3e to the 2n over e to the 2n plus 4e to the n over e to the 2n plus 1 over e to the 2n all over e to the 2n over e to the 2n plus e to the minus n over e to the 2n. And then just like every other time, I'm going to simplify this before I try and figure out what's going on. The limit as n goes to infinity, 3e to the 2n over e to the 2n is just 3. Okay, e to the n divided by e to the 2n. When you divide things with the same base, what do we do with the powers? Subtract. And n minus 2n is negative n. So you could write this as 4 times e to the negative n. And same deal here. 1 over e to the 2n you could write as e to the negative 2n. On the bottom, e to the 2n over e to the 2n is 1. And e to the minus n over e to the 2n, if we subtract those, you get e to the negative n minus 2n is negative 3n. Now, I'll point out, I'm not a huge lover of negative powers. It's not my favorite. Even though you can totally do it this way, right? You could all probably convince yourselves that, yeah, e to the negative n is going to go to 0, e to the negative 2n is going to go to 0, and e to the negative 3n is going to go to 0. Oh, uh-huh. Because what we're getting here is we're getting 4 times e to the n minus 2n. And n minus 2n is negative n. Or 1n minus 2n is negative 1n. You can do it like this. I really like to write it like this, though. I would rather write this as limit as n goes to infinity of 3 plus 4 over e to the n plus 1 over e to the 2n over 1 plus 1 over e to the 3n. Right. Again, you don't have to do it this way. I like to do it this way because in my mind, it's easier to see, oh, well, if n is getting infinitely large, e to the positive n is also getting infinitely large, right? E to the infinity is super infinity, still infinity. And then 1 over something infinitely large, just like every other time, gets closer and closer to 0. So it's just easier for me to reconcile in my mind that all of these things are going to 0. But there's nothing wrong at all with saying all of these things go to 0. I just like this better. That's all. So I end up getting 3 plus 0 plus 0 over 1 plus 0, which is 3. So this sequence converges to 3. It's like the last sequence converges to 3. Right. So again, what I would point out here, it's really important to note that it is the highest power. It's the thing that's growing the fastest is the same. Because, for instance, not that we're doing this yet, but if you were to take the limit of this as n goes to negative infinity, not that that's something you do for sequences, because for sequences we're always thinking about n getting large, but later on we're going to take the limit as x to negative infinity. Then the thing that's growing the fastest is actually e to the negative n. So yes, in this first instance, you could totally do that. But more generally, I just always try to think about dividing by the thing that's growing the fastest. That is usually a good way of trying to attack a problem.
I have a question.
One second, Anna, but yes, I would say I'm gonna pull that back just a little bit like I did before. The thing that's growing the fastest that is in the denominator. Because if you do the thing that's growing fastest in the numerator, it might make it so you're dividing by 0 in the end, which can be hard to tell what you've got. What's up, Dana?
Is 3 the limit? What's the 3? I'm confused about what the 3 is.
This 3 here?
Yeah, is that the limit or?
Yeah, that is the limit. That is what the sequence converges to, which is its limit.
Thank you.
You're welcome. All right. What time is it? Okay, we got a little bit of time. Okay, let's look at a couple more examples. Did I have a number there? It did. Good. Okay. Let's look at this sequence. A sub n equal to 3 to the n plus 1 over 5 to the n minus 1. Okay, I can write some terms. Bless you. A1 is 3 squared over 5 to the 0th. 9 over 1. 5, right? 5 to the 0th is 1. Anything to the 0th is 1. And then A2 is 3 cubed over 5 to the 1st. I don't really want to simplify that. A3 is 3 to the 4th over 5 squared. A4 is 3 to the 5th over 5 cubed, and so on, and so on, and so on. Every next term, I multiply on the top by another 3, multiply on the bottom by another 5. This is actually an example of what's called a geometric sequence, because each subsequent term is the previous term multiplied by the same ratio. 9 times 3/5 is 3 cubed over 5. 3 cubed over 5 times 3/5 is 3 to the 4th over 5 squared. Times 3/5 times 3/5. Let me say something or ask something. If you keep multiplying a number by 3/5, is it going to get bigger or smaller? I think it's smaller, right? Because 3/5 is less than 1, right? 9 times 3, well, so if I picked like 10 times 3/5 is 30 over 5, which is 6. And 6 times 3/5 is 18 over 5, which is smaller than 6. Every time you multiply by a number, a positive number between 0 and 1, your result gets smaller and smaller and smaller and smaller and closer and closer and closer and closer to 0. I should step aside for a second. When I say something is getting small, I specifically mean getting close to 0. When I say something is large, I mean getting infinitely large. And if something's getting really, really is going to negative infinity, I like to say it's getting negatively large. So if I say something's getting small, we're not thinking negative infinity, we're thinking getting close to 0. Reminds me of something, yeah. So here, what I would say is, oh, I've got a sequence that I'm going to rewrite as 3 to the n times 3 to the 1 over 5 to the n times 5 to the -1. And if I simplify this, I can write this as 3 over 5 to the n. And 3 divided by 5 to the -1st is 3 times 5 to the +1st, or 15. So I can rewrite my sequence as 15 times 3/5 to the n. But like I was just saying, every time you multiply by a fraction that's between 0 and 1, your result gets smaller and smaller and smaller. So the limit here, the limit as n goes to infinity of my sequence a sub n, is the limit as n goes to infinity of 15 times 3/5 to the n. Any number between 0 and 1 raised to a larger and larger in power, this is going to get smaller and smaller and smaller. This part here goes to 0. So my whole limit is 0. Which, if we think about graphing an exponential function whose base is between 0 and 1, this isn't a surprise. If I were to graph y equal to, say, 3/5 to the x, well, that's an exponential function whose base is between 0 and 1. And we know the graph of that looks like this. So as the inputs get larger and larger and larger, the outputs get closer and closer and closer to 0. But if you really wanted to, if you're bored someday and you got so much time on your hands, but if you had a moment, you could literally take a calculator and do 3/5 times 3/5 and just keep hitting enter, and it just gets smaller and smaller and smaller and smaller until it's eventually going to be essentially 0. And I know I promised you, there was a thing I promised you that I have to remember that I promised. Yeah. Let's look at another alternating sequence. Think of one that's going to work. Sure. Let's say we have the limit. And I should write the sequence first. Apologies. Let's say our sequence is -1 to the n times, sure, 2n plus 1 over n cubed plus 5. And I want to see whether or not this converges. Now, it is alternating, meaning it's bouncing back and forth between positive and negative and positive and negative. There's only one number that an alternating sequence can converge to. A multiplication. Yeah, it's a multiplication dot. negative 1 to the n times 2n plus 1 over n cubed. So I start writing out terms, and a1 is negative 3 over 1 plus 5. And a2 is positive 5 over 8 plus 5, and so on. Yeah. Specifically, the negative 1 to the n, that's the part that makes it alternate. Because negative 1 to an even power is positive 1. Negative 1 to an odd power is negative 1. And every time we increase n, it's going to go from even to odd to even to odd. So whenever you see in the sequence a negative 1 to the n, or a negative 1 to the n plus 1, or a negative 1 to the n minus 1, those are the typical ways of writing it, it's going to be alternating. And you use one or the other based on whether you want to start with it being positive or negative. Negative 1 to the n, if you're starting at n equal to 1, will start us off as negative. Negative 1 to the n plus 1 or n minus 1 will start us off, if we start at n equals 1, as positive. So here, if I want to find the limit of the sequence, well, I'm going to first look at the non-alternating part. Like I did before, when the limit of the non-alternating part was 3, and so I knew it was bouncing back and forth between positive 3 and negative 3. So here, if I look at the limit of the non-alternating part, it's going to be 2n, the limit of 2n plus 1 over n cubed plus 5. Which at this point, we could divide everything by n cubed, or we could say we have enough experience now. We know if it's a polynomial over another polynomial, and the bottom one has a higher power or higher degree, then the limit's going to be 0, because the bottom is growing faster than the top. Or we could show the work. We could divide everything by n cubed and get 2 over n squared plus 1 over n cubed over 1 plus 5 over n cubed. And then we get 0 plus 0 over 1 plus 0, which is 0 over 1, which is 0. To be careful, you get 0 over 0, you have to go back to the drawing board. 0 over 0 is not 0, it's not 1, it's indeterminate. Just like infinity over infinity is indeterminate. It means we have to do something else. But here, it's not the case. We get 0. So 0 is the only time when the only value an alternating sequence converges to, if it converges. Because what we're saying is we're getting really, really close to positive 0 and negative 0. But positive 0 and negative 0 are the same, because 0 isn't a number that has a sign attached to it. It's not positive or negative. The only real number that's not positive or negative. So if your alternating sequence is bouncing essentially above 0 and below 0, but it's getting closer and closer to 0, that's perfectly fine. So what's happening here is essentially we're starting at, think of here as 1, 2, 3, 4, 5, 6, 7, 8, whatever. And here's our a sub n, and here's our n. When n is 1, we get negative 1/2. Okay. So there's negative 1, there's positive 1. So we're like about there. And then when n is 2, we get 5/13. And 5/13, regardless of its sign, is smaller than 1/2. So we're less than 1/2. Oh, but then over here at 2. Sorry, apologies, over here at 2, not there, not you. And then when we plug in 3, it's going to be even smaller. It's going to be negative, but it's going to be smaller, right? Because when we plug in 3, a sub 3 is going to be, okay, that's 6 plus 1 is 7, and 3 cubed is 27 plus 5 is 32. 7 over 32 is less than a quarter, but it's negative. Sorry, negative. And then when we plug in 4, it's going to be even smaller, but positive. So we're bouncing back and forth between positive and negative, but we're getting closer and closer. We're zeroing in on 0. So if the limit of the non-alternating part is 0, then the overall limit of the sequence is 0. So this sequence, an equal to negative 1 to the n times 2n plus 1 over n cubed plus 5 does converge to 0. Or has a limit that is 0. You probably don't need to say both. Saying the limit is equal to a number is equivalent to saying the sequence converges to that number. Just be careful about the way you're phrasing things. Yeah, one more. Well, no, I mean, never just, I always say one more. Oh yeah, a lot of. Right, this was the one type of example of an alternating sequence that does converge. So I'll say it again. Your sequence is alternating. It can only converge to 0. Any other thing that happens, it's going to be divergent. So alternating sequences either converge to zero or they don't converge at all. Now, let me give you one more example, just so I'm not like, so you're not super like, James is saying things that aren't true. If I can change the paper here, maybe. So let me give you one more example. Let's say a sub n is, sure. Yeah, that's fine. 5 plus -1 to the n. Let's even do 5n plus -1 to the n over, I don't know, 3n plus 2. Is this an alternating sequence? Let's write out some terms and see. So a sub 1 is 5 minus 1 over 3 plus 2, which is 4/5. A sub 2 is 5 times 2 plus -1 squared over 3 times 2 plus 2, which is 10 plus 1 over 6 plus 2. A sub 3, 5 times 3 plus -1 cubed over 3 times 3 plus 2. That's 15 minus 1 over 9 plus 2. Are we alternating? So I should clarify. Alternating literally means we change signs every term. Positive, negative, positive, negative, positive, negative. We're not doing that here. This is not an alternating sequence. So I'll point out that this is not alternating. I will also point out it does converge. This definitely does converge to 5/3. So the limit, if n goes to infinity, of 5n plus -1 to the n over 3n plus 2. If we take our usual tactic of dividing everything by the highest power of n in the denominator, it's going to be the limit as n goes to infinity of 5 plus -1 to the n over 3 plus 2 over n. Now we know 2 over n goes to 0 because you've got a very small number over an infinitely large number. -1 to the n over n also goes to 0 because even though -1 to the n isn't a constant, it's either plus or minus 1. And whether it's +1 this time or -1 next time, you're going to be dividing by something that's getting super duper big. And if that's the case, it doesn't matter if it's positive or negative, really, as long as it's finite, and plus or minus 1 is finite. Finite divided by infinite, the infinite thing wins every time. And this goes to 0. There's a little bit more in that, which we'll talk about a couple classes later when we talk about the squeeze theorem. But that's going to be 5/3. Yeah, let's do one more. Here's an easy one, not easy one. Here's a interesting one. Cosine of n pi. So it is worth noting because it comes up. Well, actually, two things. Thing one, later on when we start talking, well, in fact, we'll look at another example here. Cosine of n pi is always between -1 and 1. Cosine of anything, sine of anything, always between -1. So I just want to say off to the side here, it is definitely in your interest to know that sine of anything is always between 1 and -1. And cosine of anything is always between -1 and 1. Always true. No matter what wacky stuff is inside the sine or cosine function, doesn't matter. If you're not convinced by me saying it, which I totally understand, I would encourage you to pull up Desmos and graph some crazy stuff. Do cosine of, make the inside really super wacky. And you'll see the outputs, the range is still bounded between -1 and 1. Can't get outside of that range unless you start multiplying in front by like a constant, like 5. Here specifically though, this, if you start writing out terms, you're going to get cosine of pi, and then cosine of 2 pi, and then cosine of 3 pi, and then cosine of 4 pi. Which, if you remember your unit circle, I know unit circle. Let's see, here's theta equal to 0. Here's theta equal to pi. Cosine is which coordinate? It's cosine the x or the y coordinate. Ooh, but maybe there people like, huh? So unit circle, when you want to find cosine or sine of an angle, cosine of the angle is the x coordinate associated with the point on the circle for that angle. And sine is the y coordinate. So when I go 0 radians, cosine of 0 radians is 1. When I go over halfway around the circle to pi radians, cosine of pi is -1. And then if I go pi more radians over to 2 pi, cosine of 2 pi is +1. Cosine of 3 pi, that's halfway around it. Right? Every time I add on another pi, I'm just going halfway around the unit circle again. So I'm just going back and forth and back and forth. Cosine of 3 pi is -1. Cosine of 4 pi is +1. So this is I find annoying personally, but some people really like a slicker way of writing an alternating sequence that bounces back and forth between -1 and 1. I don't think you should do it this way, but you can. I think it's kind of hiding the alternating fact. I don't like that, but it's fine. So importantly, the limit as n goes to infinity of this sequence does not exist. Right? We're just keep bouncing back and forth between -1 and 1, which means the sequence diverges. So a sub n diverges. Cool. Yeah, all right. So yeah. No, not at all. Yes. Which one are you looking at? Which section? Cool. That you were literally that. That's exactly what I was about to start talking about. So, yes, sometimes we want to find the pattern for the sequence based on being given, usually like 4 or 5 or 6 of the first terms. And usually we are going to make the assumption, unless told otherwise, that the sequence is starting at n equals 1. So let me give you a real basic example, and we'll make them harder in a minute. So let's say, finding the formula. Now, I will point out there are technically multiple right answers for finding a formula if you don't specify where you start, but we usually will. So let's start off with an easy one. Let's say our sequence is 5, 8, 11, 14, 17. All right, so every time we're increasing by how much? 3. So every time, if we increase by 3, every time, then our sequence, and I'm writing more words I really need to, must have 3 times n. For sure, because n is increasing by 1 every time, right? This really is, that's my A1, that's my A2, that's my A3, that's my A4, that's my A5. So here's what I would typically do. I would write A sub n equals 3n plus something. And then just plug in n equals 1 to figure out what I have to tack on there. So if n equals 1, A sub 1 is 3 times 1 plus, and that had better equal 5. So I better have a 2 there, which means I better have a 2 there. So A sub n is 3n plus 2. And then you can check to make sure it works for the next couple terms. If you plug in 2, 3 times 2 is 6 plus 2 is 8. Check. Plug in 3, 3 times 3 is 9 plus 2 is 11. Check. And so on and so on. So if you see a common difference every term, that is an easy get. You're like, okay, great. I'm just going to take that number, multiply it by n, good to go. Let's look at something a little more interesting. Again, if you have questions, really feel free to ask. Let's look at this one. Let's say our sequence terms were, 1/3, 4/7, 7/11, 10/14, 13, 10/14. That's sorry. I think that's 10/15. I think I made an error there. Apologies. And then 13/19. So a good test to see if you have an idea of what's happening here is, can you guess the next term? I want you all to write it down. Write down what you think the next term is going to be. Yeah, I'll give you like 15 seconds. Oops, calm down, Siri. You too, Dan. All right, I believe the next term should be 16 on top and what on the bottom? 23. Because we all hopefully can see, oh yeah, every time on top I'm adding 3, every time on the bottom I'm adding 4, which actually helps me figure out what the pattern is going to be, because I know that a sub n is going to be 3n plus something or 4n plus something. Because the denominator is increasing by 4 every time, the numerator is increasing by 3 every time. And then same deal. I don't really want to like write out the formula right before. I'm just going to think about what happens. So if I plug in n equal to 1, on top I'm going to get 3 times 1, and I want to get 1, so I need to subtract 2. On the bottom, when I plug in 1, I get 4 times 1. I want to get 3, so I need to subtract 1. So there's my sequence formula. A sub n is 3n minus 2, 4n minus 1. Cool. Yeah. So it's usually not, well, let's do one more. Let's not do that one. Let's do more exciting one. So let's say we had to, yeah, let's look at this one. Let's say we have terms that look like, that's not very exciting. Let's say we have -5, +5/4, -5/9. Oh, I didn't mean to do, oh, fine. Well, it's too late now. I wanted to make it more complicated. Oh, well. Oops, can't do that. -5, +5/4, -5/9. Well, one part's really easy. The numerator is going to be 5 for sure, right? A sub n, the numerator is definitely going to be 5. But it's negative, positive. So when you see the negative, positive, you're thinking, oh, it's going to be alternating. So let me ask you, is it going to be, I don't know what's on the bottom yet, but is it going to be -1 to the n, or is it going to be -1 to the n plus 1? Or n minus 1, if you like n minus 1. I think, let me see. So if I plug in n equal to 1, I would get -1 to the 1 times 5 over whatever, versus here, I would get -1 to the 1 plus 1 times 5 over whatever. But I want my first term to start off being negative, and this is the one that starts off being negative. So that's the winner. So that's the winner. So I know it's -1 to the n, not -1 to the n plus 1. But now I have to figure out the bottom. And I will point out that my bottoms, my denominators here, aren't increasing by the same thing every time. Right now, if you like, you can write a 5/1 there. And you can say, well, we've got 1, and then 4, and then 9, and then 16, and then 25. You might just see a pattern. And if you do, that's great. But if you don't, I will point out that if you look at the differences here, the differences aren't constant. The difference here is 3, 5, and then 7, 9, 11. So we actually probably could guess the next term, because the next difference would be 11, which would be 36. Now, I imagine many of you see the pattern. These are what kinds of numbers? Square numbers, right? You've got 1 squared, and 2 squared, and 3 squared, and 4 squared, and 5 squared. But what I will say more generally is that if you look at the difference of the difference of 3 and 5 is 2. 5 and 7 is 2. 7 and 9 is 2. 7 and 11 is 2. If the difference of the difference is constant, instead of having something times n, you have something times n squared, which is exactly what happened. Here we have just n squared. So our denominator specifically is going to be n squared. If n equals 1, you get 1. If n equals 2, you get 4. If n equals 3, you get 9. so on and so on and so on. It is usually in our interest to try and write the thing so that you can see what's increasing by 1 every time. So if I was trying to be more kind of formal about this, I might have written this for myself as -5/1 squared, +5/2 squared, -5/3 squared, +5/4 squared, just to see, oh, that's the thing that's increasing every time. So that's going to play the role of n. Where's time? Okay, we got some time. Let me look at these here. Let's see. Are there any that are really kind of extra terrible? I feel like most of these are not so bad as far as no, they're really like, I don't feel like we spend a lot of time trying to find the formula for a sub n. Like there's like a couple problems here. I don't know. You guys are asking all the right questions. So that's exactly what I was going to say next. So unlike these sequences where the formula for a sub n is explicit, meaning you can just write a sub n equals some stuff with n's in it and find every term. Like, so for example, I will just point out, if I wanted to here, knowing that this is the formula, I could find the 100th term of the sequence. I could say that a sub 100 is -1 to the 100th power times 5/100 squared. I could actually simplify it because it's not that terrible. That's going to be +5/10,000. I don't really care, but the point is I can find whatever term of the sequence I want without having to have any other prior knowledge. And that is not true for a recursive sequence, because for a recursive sequence, to find the next term, you have to have known the previous. So recursive sequences are typically defined in a way where the next term is a function of the previous term. For example, these are also called difference equations, by the way. I don't think your teacher is calling them that, but just so you know, I think that term pops up in the book. Let's look at an example. Let's say we have a sub n plus 1 equal to 1/2 times a sub n plus 5. And typically with a recursive sequence, you have to be given the initial value. So let's say we're going to start with a sub 1 equal to 4. And so I can start finding some terms. Now, usually for recursive sequences, often the terms get gnarly. They are not always super nice. My second term, so to find my second term, a sub 2, I'm going to plug in n equal to 1. Right, because I'm going to do a sub 1 plus 1, which is a sub 2, and that's an equal 1/2 times a sub 1 plus 5. But I know what a sub 1 is. A sub 1 is 4. I'm going to plug that in and I'm going to get 1/2 times 4 plus 5, which is 9/2 or 4.5. So that's my second term. And now I can use that second term to find the third term. But I will point out here, unlike the previous example, I can't find the 100th term of this without finding the 99 terms that come before it. I have to find each term to get the next term. There's no other way to do it usually. My third term here is going to be, okay, so it's going to be 1/2 times my previous term plus 5, which is 1/2 of 4.5 plus 5, which is 9.5/2. Not my favorite. That's 4.75. And we can keep going. I don't really want to keep going, but I will. So the next one's going to be a sub 4 is going to be 1/2 times a sub 3 plus 5, which is 1/2 times 4.75 plus 5. I will point out every time we're essentially taking the average of our number and 5. So if we, in the beginning, we were 1 away from 5, and we took the average of that, and the average now we're 0.5 from 5, and now we're 0.25 from 5. Every time we're actually cutting the distance to 5 by 1/2. So this next one I know is going to be 1/2, which is an 8, which is 0.125. So I'm going to get 4.875. And the next one's going to be a 1/16 away from 5. So it looks like, although it's harder to show, that the limit as n goes to infinity of this sequence is equal to 5. It is, but it's kind of hard to show it. Just wondering how much you have to be worried about that. No, they're not really asking you to do that at all. But it's neat. Sorry, I'm just trying to think about this in the context of your homework here. Yeah. Oh, okay, we do this later. Okay, and it's worth, yes, I should, okay. So typically, the way you try to figure out what the limit could be, well, let's pretend the limit exists. Let's say we think the limit exists. And let's call it capital L, because that's the usual choice. What we're saying is the limit as n goes to infinity of a sub n equals L. But you know what? It doesn't matter if you start at a sub n or at a sub n plus 1. If you go one more term, you're still going to have the same limit. So it's also true that the limit as n goes to infinity of a sub n plus 1 should also equal L. It doesn't matter if you go one more term or one more term or one more term. The limit, if the limit exists, both a sub n and a sub one more term get closer and closer to that limit. So here's what we do with this. We say, okay, well, great. I have a sub n plus 1 equal to 1/2 times, I'm going to run out of the room here, a sub n plus 5. Sorry, plus 5. I'm going to take the limit of both sides. And I would say, hold on for just a minute and watch for 1 sec. If I take the limit as n goes to infinity of a sub n plus 1 equal to the limit as n goes to infinity of 1/2 a sub n plus 5. All right, now the limit as n goes to infinity of a sub n plus 1 is L. And the limit as n goes to infinity of 1/2 times a sub n plus 5. Well, the a sub n part there, that is also going towards L, right? We just said the limit of a sub n is L, so that's also going to be L. So here's what we end up writing down. It's kind of neat. Every a sub whatever, a sub n plus 1, a sub n plus 2, if there was a sub n plus 2 in there, we replace it with what we think the limit is. We say, okay, great. L equals 1/2 times L plus 5. And now we're just going to use our algebra skills to solve for L. Multiply both sides by 2. 2L equals L plus 5. Subtract L from both sides. 2L minus L equals L plus 5 minus L. 2L minus L is L. L minus L is 0, and 0 plus 5 is 5. Oh, look, we got what made sense. So this doesn't prove that it's the limit. What this process does for us, it gives us a good guess as to what the limit might be. But I will tell you, sometimes this process gives us guesses that don't work. Sometimes this process gives us multiple guesses, and one of them is the right answer, and one of them is not the right answer. Because you can only ever have, how many limits can you have? If you're taking a limit of a sequence, how many answers can you get? Just one. You can only ever have a sequence have one limit. So if you've got 2 possible answers, only one of those, or maybe none of them, are right. Let me show you another. Yeah, we got 12 minutes. Again, just if you're new, if you need to leave early, you're always welcome to leave early. So if you got to take off, you're always welcome to leave. You don't have to explain yourself or ask. Just be like, hey, Jim, or didn't even say anything. You just leave. Yeah. So, yeah, let's look at this one. Let's look at a sub n plus 1 equal to the square root of 2 times a sub n. And again, we have to give a starting point. If someone gives you a recursive sequence and they don't tell you the starting point, you need to know what it is. You need to ask for it. So let's see. A sub 2 is going to be the square root of 2 times a sub 1, which is just the square root of 2 times 3. Yeah, that doesn't seem so bad at first, but then the next term is a little less nice. A sub 3 is the square root of 2 times a sub 2, which is the square root of 2 times the square root of 6, which, having looked at this work before, is approximately 2.21. And the square root of 6 is approximately 2.45. Now let's find one more term. A sub 4 is the square root of 2 times a sub 3, which is the square root of 2 times the square root of 2 times the square root of 6. That just seems gross. It's approximately equal to 2.10. So it looks like, if I had to guess, I would guess our limit might be 2. Maybe AN converges to 2. But the way we check to see if that's even a reasonable guess is we do the same thing. We're going to take our sequence, our recursive sequence, AN plus 1 equal to the square root of 2 times AN, and replace every A sub n or n sub n plus 1 with L. So replace A sub n plus 1 and A sub n with L. So L equals the square root of 2L. And then we're going to solve for L using whatever algebra we need to use. I'm going to square both sides. L squared equals the square root of 2L squared. So I end up with L squared equals 2L. Bringing everything to the left, L squared minus 2L equals 0. Factoring out L, I get L times L minus 2 equals 0. So there's 2 possible solutions. Either L equals 0 or L equals 2. It doesn't look like 0 is the answer here. It looks like 2 is the answer here. This limit does converge, or the sequence does converge to 2. I will point out one second. Technically, potentially, it's possible that if we picked a different starting place, it might have converged to 0. I don't think that's actually true in this particular example, but generally that can be true. Question, Maria? It's all right. Sure. L is the limit. So L is the thing that we think is the limit. No, it's not supposed to go. It's saying, so I've got my recursive sequence here, right? And all I did was I said, I'm going to substitute in for AN plus 1, L. And for AN, also L. Because if the sequence converges to L, basically this limit L, or both 0 and 2, which are not both the limit, those are what are called fixed points. Because if you plug in 2, let me ask you, if we plug in 2, what do we get back? What's 2 times 2? What's the square root of 4? So if we plug in 2, we get 2 back. What if we plugged in 0? What's 2 times 0? What's the square root of 0? If you plug in 0, you get 0 back. The same thing is true in this previous example. If I plugged in 5, what's 5 plus 5? What's 1/2 of 10? We get 5 back. So what you're doing when you do this process is you're finding the things that are called fixed points. Or there's another word for it. And the fixed points are the things that are candidates for the potential limit. They're not all going to be limits, right? 0 is not the limit here, but they might be the limit. Well, because I looked at the terms. But you're right, it's not very precise. I'm not doing a good job of like, oh well, yeah, clearly it's not 0 because they're getting closer to 2. But I don't think there's more math we could do to say like you can show that this is never going to be less than 2, but we're not going to really be asked to do that. So I'd say the thing you want to kind of, for these recursive sequences, the thing you want to pay attention to are these fixed points, because later on in 17B and 17C, they are going to be important. It's actually kind of all the sequence stuff we're talking about, the fixed point thing here is maybe the most important thing in future quarters. So let me point out one more. I got time. Let's say, yeah, here, okay, I got time for disappointment. Sure. Let's say our sequence was this. And we're going to start with A sub 1 equals 1. So let's find the next few terms. So A sub 2 is going to equal 4 over A sub 1, which is 4 over 1, which is 4. And A sub 3 is going to be 4 over A sub 2, which is 4 over 4, which is 1. Now I'm back where I started, which means if we think about it, the next term should be what? Right, thank you. Exactly. The next term is going to be 4 over 1, which is 4. What's the next term going to be? And then 4, and then 1, and then 4, and then 1, right? You're just bouncing back and forth between 1 and 4, 1 and 4, 1 and 4. So based on that alone, we can tell that this sequence doesn't converge. It is oscillating between two values. So I would say that this sequence diverges. Now I will point out that if we had started in a different place at one, so if you started at a fixed point, the sequence always converges. If you started at a place where nothing's changing, it's convergent. What I mean by this is, well, I'm going to plug in L for each of those things. So L equals 4 over L. Multiply both sides by L. L squared equals 4. So what could L be? 4? -2. Yeah. I would say I plug in L to try to see what the limit could be. So if the limit existed, the limit could either be 2 or -2, and those are the only options. That's it. Here it's not going to work out, but I will point out that if instead I had defined the sequence, it's not going to be very exciting, but if I had defined the sequence to be, say, an plus 1 equal to 4 over an, and a sub 1 equals -2, then the sequence converges to -2, because a sub 2 is 4 over -2, which is -2. And a sub 3 is 4 over -2, which is -2. And I think you can see where this is going. Every term is -2. If every term is the same thing, the sequence definitely converges to that one value. So if you pick the right starting point, it might converge. But generally, no. So what I would say is we plug in L for every a sub n to find the fixed points, also called the equilibria. That's the word I was looking for. And the equilibria are, I will say this again, potential candidates for what the limit could be. But neither of them might actually be what the limit is depending on where you start. Or one of them might be depending on where you start. But you can never have more than one of them be the limit. But they could be different values depending on where you start. Let me show you just one more example. I got time for one more example. That was number, yeah. So one more example here. Let's say we have that a sub n plus 1 is equal to 12 divided by 1 plus a sub n. And I'm going to start with a sub 1 equal to, let's say, not very exciting, sure, 1. And then a sub 2 is 12 over 1 plus 1, which is 12 over 2, which is 6. And a sub 3 is 12 over 1 plus 6, which is 12 over 7, which I don't know what that is. It's approximately 1 point something. And then a sub 4 is 12 over 1 plus 12 over 7, which is approximately gross 4.42 approximately. So, okay, I don't have a real good idea because I was 1 and then 6 and then 1.7 and then 4.4. I'm guessing I'm probably going to be something lower again, but not quite as low. In fact, if we do that, I will tell you the next one is approximately 2.21. And the next one is approximately 3.73. So let's go ahead and think about or find what our potential limits are. So potential limit, we're going to take this and replace them with L. So we've got L equal to 12 over 1 plus L. I want to get rid of that denominator. So I've got L times 1 plus L equal to 12. Multiply it out. L plus L squared equal to 12. Bring everything to the left and write it as L squared plus L minus 12 equals 0. And that factors as L plus 4 times L minus 3. So what are the potential values we get? Our limit could be -4. Not, right? Every value has been positive so far. And there's no way to take a positive input here and get something negative out. 12 over 1 plus a positive number is going to be a positive number. Or it could be positive 3. And that seems pretty likely. It seems like we're bouncing back and forth between being below positive 3 to above positive 3, to below to above, to below to above, and so on and so on. So if I had to guess, and it is something of a guess, I would guess the limit of the sequence is 3.